Thank you, Matthias, for the introduction, and I want to thank the organizers for organizing this event. Mathematics or machine learning, this is a very important subject right now, very promising too. So I want to present a view of machine learning from continuous viewpoint, being a PD kind of a person, character observation kind of a person, like to see everything continuous to start, and then you discretize. This is sort of a traditional numerical analysis viewpoint. And this is a joint work with two of my former students, Chao Ma and Lei Wu. And most of the work I'm presenting actually comes from this paper, which was posted at the end of last year. So let's start with some typical examples of machine learning. So the first example, this is a standard supervised learning, where you're given a set of data, finite set of data, where the label yj is given by an unknown target function f star. And from the data, you want to learn f star. You want to learn f star such that this so-called population risk, this is a definition of population risk, is minimized over the set of functions which you call hypothesis space. So this is our goal. We want to minimize this function, where mu is the distribution of the data x over some sort of a hypothesis space. And that's supervised learning problem. And another problem typical in machine learning is dimension reduction. We're given a set of data, now there's no label, and this data lives in a high dimensional Euclidean space. And we want to find a mapping from high dimensional Euclidean space to a low dimensional, much lower dimensional Euclidean space, such that this mapping preserves the most important features of the original data. So we have to specify what we mean by best preserves all the important features. So that depends on specific models. One particular model is autoencoder. In that case, you also try to construct some sort of, almost like a pseudo-inverse map. Namely, you want to, construct a map psi from this space to this space, so that the reconstruction error, so this is sort of the reconstruction error here, is minimized. So this is the autoencoder. There are other versions of dimension reduction. So these are standard machine learning problems. We're always given a data set. So now here are two examples of non-standard machine learning problems for which we don't have a data set given beforehand. So one example is a quantum many-body problem. So here we're looking at a Hamiltonian operator, kinetic energy, potential energy. We want to construct the ground state of this Hamiltonian operator. So we do that by minimizing the Rayleigh quotient. And this Rayleigh quotient can also be expressed as, in this way. So why do we prefer this? So here the probability distribution is constructed from the phi here, the state here, by this way. So this is normalizing factor, and this is the probability distribution. So we prefer to write this in this form because this is in expectations. And that's very important, as we'll see in the future. Of course, in real quantum mechanics, the wave function phi is constrained also by polar exclusion principle. So if you're talking about electrons, phi needs to be anti-symmetric functions. So that's one example. Another example is stochastic control problem. So this is a dynamical system of discrete dynamical system where this guy is the IID random noise, Gaussian random noise. Here, S is the state of the dynamical system, and A is the control at time t. So we want to minimize the control so that this objective function is minimized. We want to, in particular, we're interested in looking in the feedback control, where the control is a function of the state. So these are two problems which are not standard machine learning problems, but we want to solve them using machine learning. So these four examples, two standard, two non-standard, are the kind of examples we have in mind. Now, another very important feature for machine learning is that we always have to think about high dimension. This is extremely important, so I want to emphasize this point. So the kind of, here, for example, quantum many-body problem, the dimensionality is 3 times the number of quantum particles. So if you have a million electrons in your system, which is not a big system, then your dimensionality is 3 million. So we have to think about these kind of problems in our mind. Now, if we look back at all the kinds of problems we've looked at in high dimension, there's only one example for which is very well studied, and that's in high dimensional integration. That's the one example that's very well studied in mathematics, statistics, and particularly statistical physics. So here's an example. We want to compute this integral over the unit cube. If we use standard quadrature, we want to approximate this by this sum. If we use a standard quadrature, for example, trapezoidal rule or Simpson's rule, in which case these xj's would live on a regular grid, you would have these kinds of error estimates. And what's important in this error estimate is that there is a 1 over d in the exponent of m. So what does that mean? That means if alpha is equal to 1, well, in quadrature, usually alpha is not equal to 1. So alpha is 2 or 3 or 2 or 4, for example. But let's say if alpha is equal to 1, if you want to reduce this error by a factor of 10, your m, the number of quadrature points, has to increase by a factor of 10 to the d. If d is 3 million, as we just mentioned, this would be a huge number. This would be impossible. And this is the curse of dimensionality that has been an obstacle for many, many problems that in science and scientific computing. If instead we use Monte Carlo, then we get this exact relation for which you notice two things. One is that there's no 1 over d here. So the convergence rate is independent of dimensionality. That's very, very important. You get this 1 over m, so which means their error is like 1 over square root of m. So that's one thing. The second thing is that the error constant is the variance of the integrand. Now in high dimension, this variance can be very big too. Can be exponentially big. So that's why we need to do variance reduction. So Monte Carlo method, to a large extent, is really about variance reduction. So these two things we have to keep in mind, because we're going to use this as the benchmark for machine learning. We want to achieve error estimates for which there's no dimensionality dependence, and we want to make an error constant as small as possible. So this is the main two objectives in machine learning. So I'm not going to talk about this, but in the theory that we have developed, we have established the following: that there are sequence of machine learning models going from random feature model to shallow neural network to deeper neural network, multi-layer neural network to ResNets, in which all of them satisfy this kind of error estimates, and these constants, error constants, are getting smaller and smaller. For example, the error constant for the random feature model is bigger than the one for the shallow neural networks, and the ones for the shallow neural networks are bigger than the ones for the ResNet. So this partly justifies why ResNet is sort of performing the best among these modern machine learning models. But that's not something I want to talk about. I want to talk about a different thing. Namely, we want to formulate nice continuous problems, then discretize to get concrete machine learning models. Now, part of the motivation for doing this is that if you look at machine learning, on one hand, it's extremely powerful. It's helped to solve lots of problems that we didn't dream to be able to solve before. But on the other hand, it's also very subtle. You have to tune the parameters very, very hard in order to get nice performance. And that's not good. We don't want that kind of a very subtle, fragile performance. We want to have nice and smooth performance. So that's the motivation for doing this continuous formulation. But okay, so one question is, what do we mean by nice here? Now, if you're looking at PDE problems, then nice means that your original problem has to be well posed. If we are solving the ill-posed problem to begin with, you expect trouble. So here, we don't really have a well-defined notion of something being nice. So what we have in mind is that the variational problems that we're going to formulate have rather simple landscapes. By the way, I forgot to mention that the calculus variation problems, which are closer to the ones we're going to deal with, nice there means you have some sort of a convexity. So, for example, convex, quasi-convex, rank 1 convex, all kinds of convexity, and also you have low semi-continuity. So that's the notion of being nice in calculus variation problem. We're going to formulate variation problems too, but it doesn't seem like these guys are the relevant notion for being nice in the machine learning context, but we'll see that. So the first thing, in order to do this, in order to first formulate a continuous versions of machine learning, the first thing is how do we represent a function? Okay, so let me give you an example. Fourier transform is one of the most common way to represent a function. That's Fourier transform. Now, if we discretize Fourier transform, then we usually do these, grid-based FFT type of Fourier discretization, in which case these omega j's lives on a fixed, usually uniform grid, and in that case we have this kind of error estimates, and where this is solvable space. This is L2 to the solvable space, solvable norm. So we see immediately that this factor here, which signals cursive dimensionality, which is what situation we encounter. If you use Fourier methods for high dimensional, solve high dimensional PDEs, you have the issue of cursive dimensionality. So we don't want to do that. This is no good. So instead, what we wanted to do is to replace this by a small modification, replace this part by a probability distribution. In that case, we can write this as an expectation. Okay, so now if we discretize, we can do Monte Carlo, and then we get these kinds of error estimates, which there's no cursive dimensionality, as we mentioned before. Now this guy, this FM, the Monte Carlo discretization of this expectation, it's in this form where omega j is an ID sample of pi. Of course, we can also write this as this, where sigma is e to the iz. Sigma is this function e to the iz. And then we just write aj in terms of a omega j. This is nothing but a two-layer neural network with this particular activation function. So I think this is a very important motivation for us. So instead of having function representations like this, we'd really prefer function representations like these. In other words, as an expectation. So now we generalize a little bit. We're not going to use that activation function. We can use more general activation function, for example, ReLU, your favorite activation function. And then we consider function representations of this form, which can be expressed as expectation, as we just saw. We can also lump A and omega together as a random variable and write this as a more general form of, some of expectation. So here A is part of the random variable now. So these are kinds of expectation we want to consider. Theta here denotes the parameters we want to optimize. So out of all these A's and W's, rhos and pi's, we designate some part of these variables as parameters. For example, we can fix pi, and just designate A, the function A, as a parameter. And this is some sort of a feature-based model where sigma is a feature, fixed set of feature. So that's one, as we'll see, this corresponds to random feature model. And alternatively, we can designate this probability distribution rho as the operator as the parameter we're going to optimize with. In that case, we're going to recover two-layer neural network model. So this I'll explain later. Or we can designate A and pi. So A function A and pi, the probability distribution, as the parameter, and then we arrive at some sort of a new model. So this is the kind of representation we have in mind. So having that kind of representation, the next thing to do is to discretize this. So how do we discretize? So one way to discretize is to discretize pi by this empirical distribution, for which the omega j, for example, lives on a uniform grid. So in that case, we fixed the pi already. This is the pi. We only optimize with respect to A. So this is nothing but the Fourier method, the spectral method we are very much used to. Our trial function takes down this form where we optimize these guys. And omega j, Wj is fixed on a uniform grid. So this is the Fourier method. So in this case, the strategy is nothing but some sort of a nonlinear finite element method. So okay. That's one way to do it. The second way to do it is that we're going to discretize row, for example, this row here, by this empirical probability distribution, for which these guys will be optimized. In particular, omega j would be optimized. By the way, I should have called W. Wj should be optimized. So in that case, we get this. Looks very similar to this, but carries very different meaning. Here, both Aj and Wj are parameters to be optimized. This is, as I already said, this is the neural network model. We can optimize using, for example, limited memory BFGS. So this is very much like a numerical analysis, except that we use neural networks as trial functions. And this is like meshless numerical method. Now, this would work for many problems, but if you have truly large data sets, if you go back to the beginning, so here we have these data sets. If these data sets are truly very, very large, millions of samples, then this strategy, discretize and using traditional BFGS conjugate gradient, that kind of algorithm to optimize is not a good strategy. So in this case, we really need to use stochastic algorithms. So in order to do that, first of all, we need to express all the objective functions as expectations. And we've already done that. If you look at the example, as I mentioned, all the objective functions are expectations, okay, are all expressed as expectations. Why do we do this? Because if the objective function is an expectation, then we have the option of doing stochastic algorithm. For example, the simplest one is stochastic gradient descent. And this is a build upon gradient descent. So if I have an objective function like so, is an expectation, gradient descent will be this. Okay, so here, each step, you have to calculate this gradient. And to calculate this gradient, you have to calculate the gradient of this expectation. And in practice, this expectation is replaced by your data set. So if your data set has 1 million samples, then this will be a sum of 1 million terms, and that's expensive. The stochastic gradient descent is a small modification of this guy. Instead of calculating expectation, we just sample one term out of this expectation. So that's a stochastic gradient descent. So that's a reduction by a factor of 1 million right away. So this is the preferred methodology in machine learning, because machine learning typically have to deal with very large data samples. But you notice that going from here to here is not such a big jump, at least symbolically. So we're going to focus on gradient descent, because if we know how to do gradient descent, we know how to do stochastic gradient descent. So that part we actually not to talk about very much. So we're going to focus on formulating the correct gradient descent algorithm, for which looks trivial here, but for more complicated models, it's less trivial. This is what I want to talk about. How do we define gradient flows? So here, I'm going to sort of draw an analogy with statistical physics, non-equilibrium statistical physics, for which there was a paper written a long time ago by 2 very distinguished physicists, Nobel Prize winner, here, on how to define, exactly how to define gradient flows. So in physics, we don't speak about population risk, we speak about free energy, which is our population risk. So we want to minimize this population risk among all functions that looks this form. The parameters we're going to minimize with are either A or pi or both. Okay, but A and pi are very different kind of parameters. For example, pi is a probability distribution. As a probability distribution, the total integral has to be 1. A does not have that constraint. So in the terminology of statistical physics, this will be called non-conserved order parameter. This will be called conserved order parameter. For non-conserved order parameter, we just use the standard L2 gradient descent. And for the conserved order parameter, we have to follow this recipe. We first have to calculate V, which in physics is called chemical potential. From the chemical potential, we get the velocity. From the velocity, we get the current. From the current, we get the continuity equation. This is the continuity equation. And that defines the correct gradient descent dynamics for a conserved order parameter. By the way, For PD people, you would recognize this is how Allen-Kahn equation is obtained, and this is how Kahn-Heater equation is obtained. And for people who are really doing PDEs, you would also recognize that this is nothing but the gradient flow in a Wasserstein metric. So I give you these two examples as different kinds of gradient descent dynamics according to different kinds of order parameters. So now we're going to look at some concrete examples. The first example is feature-based model, as I already mentioned. In this case, we fix pi, the probability distribution, and optimize only over A. So in this case, we would just take the Kahn-Heater equation, Allen-Kahn equation. This is a standard L2 gradient flow. Then you get this equation. If you plug in everything, you get this equation. So here, K is some kind of a kernel, and F is a function defined here through the target function. So this is an integral equation, linear integral equation, as a matter of fact, with a symmetric positive definite kernel. So for these kinds of linear integral equation, everything is very easy. There's an extra Lyapunov function that strictly decays, not necessarily strictly decays, from which we can get the kind of estimates we want. In particular, you'll see that the risk, population risk, decays like 1/t with no cursive dimensionality. So that's very nice. Now let's take another example, the conservative case. In this case, we look at sorry, where do we go? We look at this particular model, and as a matter of fact, for notational ease, we're going to look at a slightly generalized form of the representation. So phi is a general function of x and the feature vector u, and the feature vector obeys the distribution rho, which is the target, which is the parameter we're going to optimize with. And then we go through the ritual of defining the gradient flow. Then we get this kind of almost PD-like equation where V is the chemical potential and defined in the following. Chemical potential is just the L2 variational derivative, and it's given by this expression. So this is not exactly PDE because this is the integral form. Now this equation is exactly the same equation as the one derived by several groups of people. You saw that in Josette's talk a couple of hours ago. And they obtained this equation by studying the continuum limit of two-layer neural networks. Here we get this equation by just taking the standard gradient flow from a continuous viewpoint. The important fact is that this guy, being a gradient flow on a Wasserstein metric, the right notion of convexity is displacement convexity, and that's not satisfied for most machine learning problems. That's why analyzing this PDE is still very hard. So that's the second option. The third option is let's take both A and pi as order parameters, where A is conservative, pi is non-conservative. A is non-conservative, pi is conservative. Then for A, we do the standard gradient, L2 gradient flow. For pi, we do the conservative gradient flow. Then we get these coupled system of equations. In this case, it's neither. It's not going to be similar to neither neural networks or random feature models. So this is a new kind of a model. So this is the first new model that we see from this continuous approach. The next thing is that we need to discretize. Okay, we discretize. First of all, we have discretized the variational problem. For example, the population risk, which was the integral or expectation, can be discretized into just empirical risk that becomes a sum using the data we are given. So that's a trivial step. So population risk is discretized into empirical risk. Expectation is discretized into a sum using the data, training data. So that's trivial. Next we discretize the gradient flow. So here we have several options. We can do spectral method, as we saw before, Fourier method. And this is very effective in low dimension. So even though the whole thing is, high dimension is very important, it doesn't mean that, in low dimension, machine learning is useless. Machine learning can be very powerful in low dimensions too. So in that case, spectral method might be the preferred choice. So that's one way to do it. The other way to do it is the particle method. Why particle method? because the particle method is the dynamic version of Monte Carlo. We all saw Monte Carlo is very important for high dimension, for sampling, but in the dynamic version of Monte Carlo is particle method. Or we can do smooth particle method. For those of you who did fluid mechanics, this is the analog vortex blob method invented by Turing. Okay, so we're going to see that if we discretize the kind of models, some of the models we discussed earlier, using particle method, we're going to recover standard random feature neural network models and resonance in machine learning. But if we discretize using other methods, we're going to recover new models that has not been seen before. So let's see how particle method works out. So if we use particle method for feature-based model, this was the sort of the integral equation we saw earlier. Discretizing by particle method means we replace this probability distribution by this probability distribution. By here, Wj is fixed. It's a random sample of a fixed known probability distribution pi. So here pi is given, is known. So we just sample that pi probability distribution, and then approximate pi by this. So in that case, the only parameters we want to train is these guys, the evaluation of A at these fixed randomly sampled set of omegas, W's. And then this PDE after discretization becomes this set of ODEs. And this set of ODEs is nothing but the gradient descent dynamics for the random feature model, for this random feature model. And then let's look at this conservative flow equation again. So now we discretize rho by a particle method, meaning replace this by this empirical distribution. The UJs are the ones that needs to be optimized, needs to be trained. So if we denote the loss function to be the population risk, but restricted to these kinds of functions, hypothesis space trial functions. And then the following observation, we have the following observation, namely, given any set of initial data, okay, the solution of this PDE at later time is also given by the exact solution is given by this empirical distribution with these particles following this dynamics. Okay, so the exact solution is also a finite term, M term empirical distribution, and with the atoms here obey this ODE. And this ODE is nothing but the gradient descent for two-layer neural networks. So in this case, we recover exactly gradient descent dynamics for two-layer neural networks. So now so why is this better? So I want to make just one remark about why doing this is better than doing the kind of stuff people were doing before. So first of all, what's the difference between what we're doing now and what people do standard practice in the literature? So standard, the difference is very small. It's actually how to use the trial function, how to define trial function. So this is a standard practice. And this is what's proposed from the continuous viewpoint. And this is the same as mean field. Okay, now the only difference is this factor, 1 over m here. If you think about approximation theory, this factor doesn't make any difference. You can lump them into here. But if you think about gradient descent dynamics, this factor makes a huge difference because the dynamics, gradient descent dynamics is different. I'm going to talk not about the formality, but let me give you some numerical results. So these two results here are using the result of a test error of using these two kinds of different gradient descent dynamics for a very simple target function, the target function of one neuron, just one neuron. If you use the standard practice, you get this picture here. And if you do sort of continuous or mean field, you get this picture here. So what's the difference? In here, you see clearly a phase transition between this regime and this regime. As a matter of fact, in this regime, the error is very large. In this regime, one can show, at least when it's very over-parameterized. Oh, by the way, this is the number of parameters, logarithm of number of parameters. This is the number of samples. So here you have a lot of sample. Here you have a lot of parameters. So over-parameterized regime would be here. This would be the over-parameterized regime. And this over-parameterized regime, it has been shown that the neural network model becomes degenerate to a random feature model. So the test error is large. So we have this large region where the test error is large. Whereas over here, everything is smooth. So there's no phase transition. So this phase transition is one example of kind of subtlety that people experience in standard neural networks. If you're unlucky, if you choose your network structure that falls in this regime, then your performance would be so great. Whereas here, it's not so important where you put your parameters. So that's one of the examples why doing this continuous formulation is better than doing this, since it becomes less subtle. Okay, so let me now look at another way of representing functions. That is, we represent functions by solutions of ODEs. So we take this ODE and initial condition Z, initial condition X, the flow map defines a nonlinear map. And if we contract the nonlinear map by a vector, we get a nonlinear function. So this is a nonlinear function. Fx is equal to alpha transpose alpha inner product with Z. So we're going to take alpha to the vector with one, components one. So this is the way of getting nonlinear functions. If you choose a lot of G, and then you get a lot of nonlinear functions, F. So the question is, how do we pick G? So how do we pick G? Okay, now I claim the correct form of picking G, I'll finish in 5 minutes. The correct form of picking G is this form. It's actually the right-hand side is the kind of form we saw earlier. This is exactly the form of function we saw earlier, but now we use that as the right-hand side for this ODE. So I claim this is the correct form. So never, I'll give an argument in the next slide, but suppose now we use this form as our G. So then we are looking at probability distributions of this kind. We're looking at a dynamic system of this kind, where these parameters are, either A, this family of functions of A, the family depending on parameter tau, or the family of probability distributions pi, or the family of probability distributions rho. So these are the kind of dynamic system we're looking at now. And as I said, here, after we solve the dynamic system, we use this to generate a function. Now, if we discretize these guys, we get the usual residual neural network model. Okay. Now, I said this is the correct form. So why is that so? So this is the correct form because if you started with a ResNet type of thing where these A's and W's are IID random variables picked from some distribution. Suppose we started with this ResNet. And you take the limit as L, the number of layers goes to infinity. In that limit, you recover these random transformations would converge to this flow. And this flow has a right-hand side. The form of the right-hand side is the right-hand side I just used. So this is the justification for picking that form of G. Now everything becomes an optimal control problem. We have this dynamical system with the initial condition here. And then the control, for example, is the parameter of probability distributions rho. Rho tau would be the control at time tau. And we just want to minimize this population risk over the possible, over these controls. So this is a control problem. Now, for this control problem, we can write down Pontryagin's maximum principle. For that purpose, we need to define a Hamiltonian. So the Hamiltonian is defined this way. And Pontryagin maximum principle claims the solutions of this control problem satisfies these conditions. So these conditions are very much like the KKT conditions in constraint optimization. So we optimize this function subject to these constraints. So these are the constraints. Now, so this is like KKT condition where these are the Lagrangian multipliers for the constraints, and they happen to be in the form of forward-backward equation. P is a Lagrangian multiplier, for example, and then and at each tau, for each tau, the optimal parameter, namely rho, solve this maximization problem. Okay, so that's the constraint. That's the maximum principle That's the Pointarian maximum principle. Now, this maximum principle, from this, we can motivate a gradient flow. Remember, we wanted to define gradient flow. This gradient flow, instead of maximizing rho for each tau, we just define this gradient descent dynamics for each tau. So this would be the gradient flow for this particular flow-based model. If we discretize this gradient flow, okay, this looks like a lot, but if we discretize this gradient flow, we get exactly the gradient flow for resonance, where this is the forward propagation, this is the backward propagation, and this is the updated parameter. So this is exactly the gradient flow for the resonance. Now, okay, now we can also, we don't have to do gradient flow. We can also cook up and formulate a numerical method directly based on the Pointarian maximum principle. That's done in this paper. You know, work with Chen Xiaoli, who's now in Singapore, and others. So this is, you know, it's very simple. That namely, we sort of, you know, we sort of at each step we solve that maximization problem for the optimal parameters, and then we solve these forward and backward equations. This is called method of successive approximation. Turns out this doesn't work so great, and you have to do some modification. And there's a technical details. You can look at the paper if you're interested, but I'm not going to skip that. I'm going to skip that. But this sort of maximum principle based algorithm, particularly this version, has some advantage compared with gradient descent based algorithm. So these are this two set of examples. This is the one situation for which you will follow the standard sort of Xavier-like default initialization. This is for a very bad initialization for which you will set everything to 0. So you can see that the performance here, this is the green line is the performance with the maximum principle based method, performs better, but substantially better in the problem with bad initialization. So it is, and these other guys are Adam, Etagrad, and stochastic SGD. So you can see the green lines has some advantage. Now, if you compare these two guys, maximum principle is this, gradient descent is this. So we can sort of, so these two things means that, so besides these are the update of, these are the update of the parameters. Besides update parameters, the algorithms also involve these forward and backward propagation. So the difference between these two algorithms is that for each forward and backward propagation, here we do this optimization, and here we don't. We just do one update of the optimal parameters. Okay, so here we iterate many times in order to get the real optimal parameters. Here we just do one update. So there's an interplay between forward and backward propagation and also optimization of the parameters. If you really want to optimize every backward and forward propagation, you would get this. And if you don't, if you just do one update, you'll get this. And you can play something in between, and that probably would give you a balance between the cost of backward and forward propagation and then optimization of the parameters. So this should be pursued, but I don't think anybody's done this. So I mentioned at one point that the continuous formulation gives the same equation in the mean field. But I want to say that these actually are two different viewpoints, even though at sometimes they do give us the same model. Now, mean field takes the statistical physics viewpoint, namely starting from a particular machine learning model, discrete model, and look at the continuous limit. And continuous is more like numerical analysis. We start formulating a continuous model and we discretize. And this has certain advantage in the sense that it allows us to formulate different models. It allows us to formulate, I think it's the most important thing is the following, that it allows us to think outside the box for machine learning. So now if you think of machine learning, it's neural networks. Oh, I should stop. It's neural networks. But that's not the necessary choice. The only choice you can have. We can have different discretization. We can have different models that I've already explained. Okay, I wasn't give you an example of another different model, but let's skip this. This is the model, feature-based, but flow-based, but random feature model. So let me summarize. So continuous formulation tried really to formulate first principles of machine learning. and it gives rise to PD-like variational problems. And the performance is more smooth. There's no phase transition. And also gives rise to new models and new algorithms. Particular new models and new algorithms suited for particular specific application. So what is the most crucial point? The most crucial point is representing the function. So you have to represent functions as expectations for things to work in high dimension. So I discussed two examples, integral transform-based and flow-based. And naturally, we want to think about other representations. And that turned out to be very hard to think about other general representations in terms of expectations. And we also saw that particle discretization, the most natural discretization that works in high dimension, gives rise to neural networks. So in a way, one lesson that I've learned through this work is that you find that neural network models are actually very natural, even though we have this way of thinking about machine learning outside the box. In the end, neural networks are very natural. But we do, even for neural network models, we do have alternative ways to formulate them so that the performance is more smooth. Thank you very much for your attention, and this is the end of my talk.